this reality of particle, this point particle that you found here, this reality didn't exist, you created it when you performed the experiment. Or matter waves. If there is a body, anything that has a momentum p, so it's moving, it always has an associated wave that has a wavelength to h by p. H is Planck's constant. Whether it's light, it's photon, or anything, or a tennis ball, or us, anything has a wave associated with it. Now the question is whether this wave is significant or not. For example, our microscopic world, for example, this chalk even, if you calculate, if you throw it, so it has a momentum. If you calculate its wavelength using mass into, so h over mv, because this is non-relativistic, right? The speed is not close to the speed of light, v, and in that case h over just mv. If you calculate, you will see that the wave that you get associated with it, it will be a wave, but its wavelength will be so small that it's much smaller than the size of the chalk. And in that case, there is no question of, wave. I mean, there is wave, but it's just useless. You can just treat this as a classical macroscopic body. Now, the question that I asked was, what kind of wave is this? The wave we have in case of water, the still water looks like this. So it's the zero level of a pond or a swimming pool. When you start a wave, it starts, the height of the surface starts oscillating above and below its steady level, right? So that height is the amplitude of the wave. In case of sound, it's the pressure that's changing. High pressure, low pressure, this is the wave around the normal pressure. So whatever the normal pressure of air in this room is, when I speak, this wave is traveling, this disturbance, and that compresses the air, and the air expands, and that's how. So around the normal pressure, so it's a pressure wave. Then photon is an electromagnetic wave, quanta of an electromagnetic wave, and so on. What about this wave? What is this wave? It has to be a wave of something. Turns out that an interpretation was given, a statistical interpretation, this is said. This has to be associated, not equal, to the probability of finding the body. So suppose you have a small particle and you kept it inside a box, okay? There is a wave associated with it, and the wavelength of that is h over p, right? If p is the momentum, then it will have a wave associated with it. It could be some lambda, okay? Let's say this is your wave. It could be any shape, just for simplicity. It's not visible because it's not a physical wave. But if you know this wave that looks like this, and this is the length of the box, it tells you that if you perform an experiment to find out where the particle is, like you start looking for the particle, then the chances of finding the particle is higher here, is very low here, 0, higher again here, okay, higher here, slightly lower here, and like that. So the shape of the wave gives you the shape of the wave gives you the probability of finding in some position. So if you are looking for, so what we do, we try to look it here. Of course, our detector is stationed somewhere, right? It is not looking everywhere. So you move the detector, or you are trying to see, for example, a better example is not just one particle in a box. You prepare exactly the same copy of this experiment. Okay? And so on. 100 such boxes. And all of them have exactly the same particle. Okay? And so you expect that exactly the similar conditions. So whatever state that particle is will be expected to be the same everywhere. Let's say the wave looks like something like this. Okay? Then you expect it looks like here also looks like this. Now you performed experiments. Here you placed your detector here. In this experiment you placed it 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 here. Okay? You're looking, you set these things. And you tried to look where the particle was. Of course it will be found somewhere. Turns out, if you have large number of copies of these boxes, when you find the particle, sometimes, for example, here, maybe you don't find the particle. You see nothing. The particle is not there. Okay? Let's say here also, here you found it. Here also you found it. Here maybe not. Here maybe not. Okay? And then you plotted where you found the particle. Then you plotted, let's say this is the x-axis, so 0 to L is the length of the box. Okay, you understand? And then the height will be the chances of where you found it. Okay? Hi. So now, kiman time paisu moi. So 100 points, you did 100 experiments, right? You looked at 100 boxes. How many times out of 100 you found them where? He will see that most of the boxes he looked, this is where it has been found the highest times. Okay? This is where slightly less, maybe here, maybe 50 times the particle was found here. In 50 number of boxes, the particle was found around here. Okay? Almost never, maybe one or twice the particle was found in this kind of situation. So what I am saying is, he looked, actually you could say, we looked everywhere. And yes, we looked everywhere. We scanned it in every box. And sometimes we found it here, sometimes not. Even here, in some experiments, it was found here. But in another experiment, it was not found here. So probability is like that. It means that, okay, there is a high chance, but it's not sure, right? When you toss a coin, it means that 50% of the time it should be heads and 50% of the times tails. That's what you expect. But it does not mean that if you toss it 10 times, exactly five times it will be heads and 5 times it will be tails. It will not be, right? It will be maybe 6 and 4, okay? But if you increased like 1,000 times, 1 million times, then you will see that it's going closer and closer to 50. So maybe 49.999, and another one is maybe, 50.0000 this way. So you will see that if you increase the number of boxes, What you see experimentally is that most of the time it's found here, slightly less time here, and even lesser here, like this. Okay? It's slightly different. This is how, so what does this mean? Like here it was found less now. So this is number. This is number of times they are found in this position. If you take this position, then here it was found this many number of times. Or in this many boxes. Here, this is very important in quantum mechanics, first time, this interpretation. So I'm spending some time and you should ask questions. এই ইন্টারপ্রিটেশন ওপর তাৰপিছত quantum mechanics will proceed. Okay. So most of the time it was found here. So this is larger, let's say maybe 60% of the time, here maybe 40% of the time, here maybe 30% of the time, like this. Okay? And some places never, some places never. So at the exact edge, it was never found. At this exact edge, it was never found, like that. So that's how they got this idea that it's related to probability. So this matter wave, the wave is related to probability. How is it related? The next question. Is it equal to probability? So let's call this wave psi. Let's denote it by psi x and t. Okay? Let's call this psi x and t. Just like any wave amplitude we represent by y or x, let's call this psi. Because it's not related to pressure that we could write p. It's not related to position, that we could just position wave. What is position wave? In case of spring, the displacement is the function, right? In case of a spring, so this is where equilibrium, if you moved it by some amount x, so if you displaced by a small amount x, then this x, this is the oscillation starts, right? So your x will be the wave function in this case, x of t, right? In case of a string, let's say y coordinate changes, so y of t. In case of electromagnetic wave, it's electric field or magnetic field, right? So those. In this case, let's call this psi, because we don't know what it is. This is the most common symbol for the wave, or this is called a wave function. Because people didn't know what this wave is, so wave function. Okay? It's a plain name. Now, when I said that it's related to probability, is it equal to probability? So P of x and t. If that was so, it's related to probability, we know that much. But we can guess that it's not equal to probability. It cannot be, because consider this wave function. A wave function can be positive or negative, like any other wave. So yes, this is good that here we found it, let's say 20% of the time. But here then this will get minus 20. And there is no meaning of like minus 20% probability. Probability is always between 0 and 100%, or 0 and 1, right? So it has to be some positive number. But physically we understand that if here we have higher probability of finding it, then equally higher this is probable, right? This is also equally probable. It could be flipped, but it's still higher amplitude. If we squared it, or at least not just square, took it mod square so that we make absolutely sure that it's always positive, then it will really represent that that here we have higher probability, here we have higher probability, and 0 here. Okay? So this is mod chi square, we guessed. So the probability is proportional to mod chi square. And in fact, right now we will not calculate what the chi is because we have not. But we told you, we found out that we can find out the wavelength of this wave. So the wavelength is related to the momentum, right? But how exactly the wave looks like, we don't know yet. So is it clear? It will not be 100% clear because this is quantum mechanics. It gets slowly better with time because it's very different from classical intuition. Because classical intuitions like waves, particles, this solidity, this is how we all grew up from the beginning. After our birth, what we see is this world, right? Everything is bigger. Everything is bigger, everything falls, particle is a solid particle, there is no uncertainty. What is a wave? Wave is something spread out, right? It's here and it's also here. But a particle is really, if it's here, then it's here. And so we either talk about a wave or a particle. We have never seen anything in the macroscopic world that wave and particle were the same thing. Okay? Wave is something classical. Particle is something classical. Now when we go to the quantum world, it's possible that the actual thing, electron let's say, is neither wave nor particle. It's something else. What it is, we don't know. But at times, it behaves like what we knew to be wave, our classical understanding, because try to understand this, that wave is something that belongs to this macroscopic world, okay, that we are familiar with. Particle is also another idea that we are familiar with, this solid, precisely located in one position. So when we look into another world, try to understand something. What do we use? We have to use what we know. So we'll try to see, does it look like our waves? Does it look like the particles? Okay, so that's why we use those ideas, and we find that no, we cannot fit an electron into either wave or particles. It's sometimes in some experiments, for example, photons, in some experiments, if you do interference experiment or diffraction experiment, you'll see that it's a wave. And then sometimes in another experiment, photoelectric effect, it behaves like bullets, particles. So it's entirely different. But you don't see them behaving both ways in one experiment. So they are something entirely else. In some cases, in some situations, they behave like our waves. In some situations, they behave like our particles. But they probably are neither of these. Okay? So, but the boy found a way to relate these two, and he said that any particle, any body, anything that has a momentum p has always an associated wave that has a wavelength of h over p. Let's call this wave psi x in t, the wave function. Matter wave to হল মানে matter wave to এটা abstract বস্তু, এই বস্তুটো কিহৰ মানে directly psi কি বস্তু আমি নাজানো। Okay, but if we take mod psi square, it's a mathematical function psi x of t. Physical meaning psi nijor physical meaning nai. But if you took mod psi square, then this becomes proportional to probability of finding. So I gave you a particle and I asked you that find out the wave function, or I gave you that, look, this particle has an associated wave function psi x of t. It has, okay? So that's this psi x of t gives you the state of the particle or its associated wave. What you can tell is that, okay, if this is so, I can tell you what is the probability of finding the particle here. If you did an experiment to look at here exactly, then you have to find out what is the value of psi x and t exactly here. Take a mod and square. Then whatever value we get will be the probability that finding the particle here. Okay? In another position, exactly, mod psi square at that position, x equal to whatever value is. If you did that, that will be the probability of finding the particle here. But when you perform the experiment, it might not be there. Okay, it might not be there. But if you repeated this experiment on same kind of room and on same kind of particle, because if you performed once this experiment, doing it again is not going to work because you already disturbed the particle. Do you understand? So I have a room, I have a chalk. Consider this to be really microscopic. We are inside an atom, okay? And everything is really small. Now, I asked you where the particle is. You perform an experiment and you found it here, let's say. Once you found it here, now it's changed. Its wave function is not anymore what it was, because experimenting means you disturbed it with some light or whatever. It's not like, looking at a duster, because it's not disturbed by light that much. It's not going to change its position when a photon hits. But an electron will. When you try to look into an atom or an electron, it will be completely in a different state. But once you found it, that is gone. That's why I told you take many boxes and perform the experiments independently so that this one doesn't disturb the other. Okay? Otherwise, you have to wait for a long time so that it goes back to its initial original wave function state. You could perform the experiment and then wait for an hour, then again perform the experiment. That might work. Otherwise, the best way is prepare copies of these experiments and perform on all of this. Okay? So when you did, you find that this is related to, so mod psi square gives you the probability really. Okay? The next thing is, what does it mean? It's very uncertain, right? It's very uncertain now. What are we talking about? We are talking about physics. We need to know really what is the state of the particle, because we always did. We ask this is our sun and this is our earth. Where earth will be after, let's say, many rotation, after 100 years. Where will be exactly earth? We were able to answer this. We solve Newton's law, Newton's equation, F equal to ma. We put the value of F, the gravitational law, and we solve. And we find exactly what? Exactly its position, whatever r in, let's say, theta. Okay? Or x and y, depends on the coordinate you choose. But once we solve this, we know the position and velocity forever. But here we are talking about, there is a chance, if you perform the experiment, it might be here, 20% of the chance it will be here, 30% of the chance it will be here. We are not really sure anymore. And what does it really mean, where it was? The question is, where was it before you perform the experiment, right? We should absolutely know. Okay, it was found here. Let's say this is a wave function. You're looking here, some A to B, okay? If you remember from your thermodynamics class, I told you about a continuous probability, that probability is proportional to how much distance, thickness you are looking at, right? So I'm walking to and fro. The chance of finding me somewhere is proportional to the length that I'm covering. So if you take really just, what is the probability of finding him just exactly at this point? 0. But if you ask like, what is the probability of finding him at least in this block? Then you can calculate it. Length of the block divided by full length, and that is your probability, right? So that's more or less like, this is the wave function square, mod psi square, this, okay? And this is x. This area will be what? Mod psi square dx. And that will be your probability. When I said related to probability mod psi square, I said this, okay? This actually is a probability density, if you remember correctly. If there is a continuous probability, then taking a thickness dx and multiplying that with your probability density gives you probability. It's probability per length here. Probability per length. So when the length is 0, like this point, your probability density times 0 is 0. That's why you get 0 probability. But if you have some thickness, then this probability density times the thickness, density times length gives you probability. Okay? So this is like, then mod psi square dx will be your probability, dp, let's say. So this is the probability, if you took this area, it will be the probability of finding the particle between A and B, right? But then you performed the experiment and you found it here. You found it here. It's absolutely possible. Now there are really 3 stands, okay? 3 opinions, let's say. Now the question we ask is, where was it before the experiment? Where was the particle? So the first view is called a realist view that Albert Einstein took. He said it was at C. There is no chance and probability and all this. It was exactly at C, he said. And in that case, if that was true, then it means quantum mechanics has problems. Quantum mechanics is not the complete picture. We need something else because quantum mechanics is unable to answer, right? Quantum mechanics is saying, oh, there is this % chance of getting it here. C had some probability, maybe 5%. But it failed to tell you where exactly it was. And Einstein is saying that it was exactly at C, that's why you found it there. And if that is so, then this quantum mechanics has problems. It cannot be the complete picture because it is failing to tell you where the particle was. The second view was orthodox view. Due to Bohr, Niels Bohr and all these people, most people, that it was nowhere. Okay, it was nowhere or everywhere. When you performed the experiment, you created this. You forced it to be at C. Okay? It could be anywhere or nowhere. When you did the experiment, you made it appear exactly at C. Sounds ridiculous, right? At least now. But that's what it was. They said, Niels Bohr and these people said, That's how it is. You created this reality of particle, this point particle that you found here. This reality didn't exist, you created it when you performed the experiment. We conscious observers exist, and that's why the world comes into reality. Third possibility is called agnostic. Agnostic is like, we don't care where it was. That's a useless question. We have not performed, so before the experiment, we only know something when we know it. When we do the experiment, and now we did the experiment, and now the particle is here. Where it was before, it's a philosophical question. Before, we did not do the experiment, so we don't know where it was. And that's why it does not matter, because it cannot be known. Okay? In science, let's say, if something cannot be known, then it's useless. What can be known is important or useful. So once we performed the experiment, it was here, found here. So now it should be here. Before that, we can't say, and we don't care. So what used to happen is like, people found quantum mechanics very puzzling and they didn't believe it. So they will argue with quantum physicists. And this is the one that quantum physicists will start to sell. Like, no, I mean, it was nowhere. It was the experiment that created your reality. It happened to be here and this thing. But if the person keeps arguing and is persistent, then they will drop to this view. Drop to, we don't care. This is meaningless question where it was. Only after the experiment it has some meaning. So, and then they will end this discussion. Okay? So nobody really clearly understood what it was. But at least, why then people are really arguing? Because this mathematics was working. At least when they were performing various experiments, they were finding that yes, it matches with the probability that quantum mechanics predicts. So maybe in this experiment it was found here. But if you repeated the experiment many times, then indeed where the particles were found, the number of times matched with this behavior, the number. And so obviously it's something serious. It's working, the mathematics. Obviously, that's why people took it seriously. But they said maybe it's not complete picture, but it's somewhere close. But Bell performed an experiment. That experiment will come maybe later in this course or maybe in your pure quantum mechanics course, because now you are not ready. Okay? So Bell actually performed an experiment, designed an experiment, and he said, whether it's 2 or it's 3, if I assume that it's 2, then the result of the experiment will be different. I mean the Bell's experiment, not this. He designed an experiment to find out whether this is true or this is true. Okay? Or if they were like same. Bell came to this conclusion after designing this experiment that if this was true, there is a different reality. I mean, his experimental result is different. If this is true, he has another result. So depends, the outcome of Bell's experiment depends on whether this is true or this is true. It's not anymore just a philosophical discussion. And he found that it's really this. So it's really this, which is very absurd, that yes, actually our experiment forces the particle to take a stand, to come to somewhere. So the wave function was like this before, it's the wave function, but when you perform the experiment, it collapses somewhere. So in this case, if C, it was found in C, it really was like this. So the wave function was like this, and then it became like this, spike. So now if this is a spike, then obviously like really almost 100% chance of finding it here and 0 everywhere. Then if you give it time, it will slowly decay back to this or something else. So the question is like, so that was the question, where will it be found if you perform the experiment immediately after this? And the answer is like everyone agreed, it will be again found at C. Because now the wave function collapsed, and this is how the wave function now is. And so it has a huge chance of being here and 0 everywhere. So immediately if you perform, you will find it again here. But if you waited, that will start decaying according to an equation that will come later. It's called Schrödinger equation. According to that equation, the wave function changes its shape over time and space. Okay, not randomly, right? This is the spike. Then what will be its form after some time? It could be this, right? It could be this. So how the shape will be is related to Schrödinger's equation. We'll come to that. So the first question is, what is the velocity of this wave? It's moving with a velocity v, and it has an associated wave, I said, h over p, which is gamma mv. What is the velocity of this wave? Velocity of the wave is simply this. Let's call this something else. Velocity of the wave, let's say, like this. Okay. So this is v equal to lambda nu is the velocity of wave. Any wave you take, frequency type wavelength is the velocity, right? Because wavelength is the length and nu is 1 over time. So yeah. Now lambda is h over p and nu is E equal to h nu. So you could take nu equal to E over h. So E over P equal to gamma, C square P is gamma mv, and so C square by V. What is this V? This V is the velocity of the particle, and this is the velocity of the wave. How much is this? So this is C square by V, that means C by V times C. So C by V is obviously greater than 1. Right? Because v is the velocity of the particle, which is obviously less than the speed of light. And this is speed of light. So this is greater than 1 times the speed of light. So turns out the speed of the wave is greater than the speed of light. Which is strange. We expect the speed of the wave to be the speed of the particle, because we are saying that the wave is associated with the particle. What is the meaning of saying like the particle is here, but the wave has, left it and gone somewhere else? That's what will happen. So what is happening here? What is happening here is that, although the associated wave is this, associated with a particle, but wave velocity or phase velocity, do you remember phase velocity and wave velocity, group velocity? So if you took two waves that has the same amplitude, two waves, another one, same amplitude but slightly varying wavelength, and you superimposed. The result was something like this. If you remember from your waves in oscillation classes, So it's like there is a wave inside, but there is a wave guide. Okay? There is a wave and there is a wave guide inside. So when you sum them, in some places they add up, and in some places they kind of oppose each other and cancel out. So in the end, what you get is this wave inside another bigger wave. So this wave going on, but its amplitude got modulated. So as a result, it becomes like this. Okay? If you superimpose many such waves with slightly varying, continuously varying wavelength, what you get is something called a wave packet. A wave packet. That's it. It's a wave, but highly localized. Just here and nothing there. You can form this using many waves, superimposing them. Take a wave y equal to, let's say, some simple case sine, okay? Kx minus omega t. Take this, and then take another one y prime, let's say same amplitude, sine k plus delta k x minus omega plus delta omega t, and add the two, okay? You will find that it will be just a simple exercise. I already did in waves, so I'm not repeating this. Just do that and simplify. You will find that and treat delta k and delta omega very small with respect to k. So what you will find is, after adding, is that some maybe cos of this delta kx minus delta omega t times sine kx minus omega t, I think. So this is your original wave, right? This a times this is your original wave, and this is another wave that is regulating the amplitude. So making it zero somewhere, it's bigger somewhere. So it becomes an envelope and inside the original wave. So turns out the Voigt wave is a wave packet. 2 cos a plus b by 2 into cos sin b a minus b by 2 এটা ফর্মুলা আছে, এটো ইউজ কৰিলে তোমাৰ এটো আহি যাব, ওকে? তাত এটা হ'ব তোমাৰ এই লগত এটা প্লাস k থাকিব. So neglect that, saying that k is here, k is much bigger than delta k, and then এটা part থাকিব আৰু এটা part এনেকুৱা আহিব. But এটো মানে তোমাৰ waves তো আছিল এই প্ৰবলেমটো, wave packetত গলে তুমি পাবা group velocity, yes. So মানে the point is তোমার group velocity formula আহিব এই যে এই বস্তুটো, then ইয়াৰ এই যে wave আছে এটো তোমার প্যাকেটৰ envelope হল, এই envelopeটোৰ speed velocity হল তোমার group velocity, right? তো envelopeৰ velocity কিমান হ'ব? del k by del omega, right? K by omega হয় waveৰ velocity, del k by del omega হ'ব তোমার envelopeৰ velocity, group velocity. Now jodi it's just two waves. If you take many waves with continuously varying, k and omega, then this discrete thing will become dk by d omega. Okay, dk by d omega. Now you know what is k. K is 2 pi by lambda. Okay, omega is 2 pi by t, right? Or 2 pi nu. This is an exercise. Tomar time শেষ হৈ গল, এই কারণে আমি তোমালোকক এতিয়া দি দিম এটো. Just do this. Replace this nu from E equal to h nu. So replace with energy. Here lambda, take it from the wave h by p. So put here h by p and here your e over h. Then you have some k and omega. You have some k and omega. And remember, put E equal to gamma mc square. And put P equal to gamma mv. So you have a gamma, V and all these things. Okay? In the end, what you have is, this will become some function of velocity. Right? This will become some function of velocity because gamma has the velocity of the particle V and all these things. This will also become some other function of velocity. It's very easy to see that it will be a complicated function. There will be square root because gamma, 1 over square root of 1 minus v square by c square and all these things. But in the end, it is some function. Now you need dk over d omega. That you can also write as dk dv d omega. So your k is a function of v. Your omega is a function of v. Calculate these two independently. Calculate this from here and this one from here. It will be slightly difficult. If you do it cleverly, it will be easy. Otherwise, it's a long algebra. Lots of differentiation and taking gamma and all these things. But please, it's easy, straightforward. Do it and then plug them here and then find out what is this Vg. What is this Vg? Let me tell you the answer. The answer will be V. As we expected, the speed of the wave packet will be equal to the speed of the particle. So really this wave is traveling with the particle.